Good evening, everyone. Today we will start with Raman spectroscopy. Okay, so the Raman spectroscopy it was being proposed by Dr. C.V. Raman from India. Okay, so before I enter into the Raman spectroscopy, let's discuss about the uh, types of spectroscopic techniques what we have talked about till now. Okay. So what was the first one? The first one was the absorption spectroscopy. Okay. So in the absorption spectroscopy, what we saw that say there is a source of light, then we have some optical arrangements from here. Okay. So this is optical arrangements. Then we have the sample in between, and then we have monochromator, and then we have detector. Okay. So from the source we get the optical radiation, and then this optical this thing um, it can sorry this is a monochromator, sorry, and this is your this thing gratings. Okay, and then we have another this thing this like gratings and prisms. Okay, which will decompose the light, and it will be then an incident onto the detector. Okay, in the monochromator also you have this thing, but there is an slit also, which is called the exit slit, and depending upon there from this exit slit, a monochromatic light initially when we are having this bulb, it is a it is having it is a polychromatic light. Okay, that means it is having light of different wavelengths. Okay, however when we put it into the monochromator which is having a slit, it breaks down, it decomposes the signal, this optical light, and through the exit slit only a specific wavelength light which is called the monochromatic light, it falls onto the sample, and then there is a filters and all these things, and through this filter we get to the detector. Okay. uh, Okay, now I'm just getting confused. This is just a filter, blocking filter. Sorry, herein we are having the blocking filter or any other filters. Filter. So we are having a filter, and which helps us in conditioning the absorbed light, and then it gets into the detector. Okay. So here we are getting polychromatic light. Then we have monochromator, which changes the light into a monochromatic light. then we have the sample, and then we have a filter system to filter out some unwanted noises. Okay, and then we have the detector. If you are using this imaging based system, then we have a similar arrangement. We have the light, then we have some filters if you want to filter out something, then we have the solution, and then we are having this gratings or prism, grating or prism, and then we have the detector. Herein the detector is an imaging sensor. Okay, so light comes in, it goes to the filter. So here it is a polychromatic light. I am writing polychromatic as PC. Here also, when the sample is being incident onto the sample, then also it is a polychromatic light. Again, when it is falling onto the gratings, it is again polychromatic light. Then from the gratings there is a decomposition of the light component. Okay, and when it is falling onto the sensor array, on each of the array, in each of the sensor, smaller sensor will be having is one or several this wavelength of radiations. Okay, so in that way we are getting the thing. So we get a image of the spectrum. Okay, like this we get an image of the spectrum where we have some lines, some dark lines, some bright lines. Okay, so this is about absorption. So what was happening in the absorption? If you see, everything is in the straight line order. Okay, so the light is falling onto the sample, and how much amount of sample, how much amount of the incident photons the sample is absorbing, we are basically calculating. This is absorption IEA based on the IT, that means the transmitted light which is being transmitted through the sample. Okay, over here also what we are doing, we are doing the same thing. So here we are having I0, the light photons which are passing through, they are it is IT, and then we have IA which is being absorbed by the solution, and that thing we are calculating. Okay, so this was in the absorption spectroscopy. In the second case, we had fluorescence spectroscopy. Okay, fluorescence or phosphorescence, I am not separating them this thing, as the principle is similar. Okay, so that was, we are basically looking into the luminescence property of the sample. Over there what we are having, we are again having the radiation source. Okay, then we were having this monochromator. I'm writing it as MC, monochromator. Okay, then this light was falling onto the sample. Now instead of taking the sample, measuring the intensity of the light directly in the straight line, we were measuring the intensity in the at the 90-degree angle. Okay, so here we were having some optical filters, and then we were having the detector. Right, now why this is so? The thing is that when we are having this light which is passing through, it is expected that the light it passes in a straight line. Okay, so the majority of the light which is being generated by the source, it will pass through, and only the fluorescence which is not following any directionality, that will be emitted in all the directions including at 90-degree position. Okay, so in that case what you are doing is that the light with which you are exciting the sample, you are minimizing the effect of that particular light. Okay, so here it was polychromatic light and here we were having monochromatic light. So MCR, let me tell it as MCR, monochromator, and here we are having monochromatic light, and this monochromatic light it is getting transferred through the sample. Okay. However, the fluorescence light which is being radiated from the samples, they are moving at all the directions, and it is expected that at 90-degree the effect of this monochromatic light, it will not it will not be going through going at a position of 90-degree, and but practically it is not possible. Some of the monochromatic light they may get scattered, and for stopping those scattered monochromatic light, we can have the filter arrangement over here. Okay. Now, in fluorescence spectroscopy, if you see, we need a system over here, or we want to we want to excite the sample at a particular wavelength, then only it will generate a spectrum at a higher wavelength. That also we have discussed. The wavelength of the fluorescent, the wavelength of the incident light, it is lower as compared to the wavelength of the fluorescence or the phosphorescence spectra. Okay. So why that is happening? We have already discussed that there is a decrease in the energy content in the of the photons which is being which is being emitted from the samples. Okay. Now, when we talk about Raman spectroscopy, it is basically not about the absorption spectroscopy. It is not about the luminescence. Why luminescence? Luminescence because both fluorescence and phosphorescence together they are regarded as luminescence. Okay. So combining these two, I am terming it as this luminescence. Okay. So the Raman's spectroscopy, it does not follow the absorption thing. We do not measure the absorption. We do not measure the luminescence. That means we do not measure the fluorescence or the phosphorescence, where the sample is emitting the light due to some due to some reaction. If it is due to some chemical reaction, then it is called chemical luminescence. Okay, so we do not measure those. Now, what happens over here? In Raman spectroscopy, we basically talk about scattering. Okay, we basically talk about scattering. So, the scattering it can be of two types: elastic scattering and inelastic scattering. Okay, so scattering is of two types. Now what happens over here in the scattering? Raman spectroscopy, we use laser source. In fluorescence spectroscopy, we may use laser source, or we may use some this normal lamps from where we can decompose the signal and we can convert the polychromatic light to the monochromatic light. Whereas in the laser, what happens? It emits, the lasers, they emit a monochromatic light. Okay, so this is one of the advantage of the laser. If we want to use a laser, the laser will always emit a light of specific wavelength or frequency, whatever you say. Now herein, if you see, we are using a laser, and then this laser is being used for the excitation purpose. Say for example, this laser, it emits the excitation light at a frequency of mu 0. Okay, so the energy of this laser light, E, it will be equal to h of mu 0. Okay, now when this is being used to excite a molecule, some of the light, it will be scattered at the same frequency as that of the incident radiation. Okay, so this is an elastic scattering. So in elastic scattering, there is no loss of energy. In elastic scattering, there is no loss of energy. Okay, and this scattering, it is regarded as Rayleigh scattering. It is regarded as Rayleigh scattering. Okay, in addition to the Rayleigh scattering, there are other scatterings also, wherein you have the energy which would be equals to h of mu 0 plus minus h of mu. Okay, so what is happening? So basically for mu 0 we are getting a frequency of this thing. So basically we will be getting some scattered lights which will be having frequency, if I say mu dash, which will be equals to plus minus mu 0 plus minus mu. But what is mu 0? Mu 0, it is the Rayleigh scattering. So across the Rayleigh scattering, you will be having at particular frequencies certain peaks. Okay, and the location of the peaks on either side, it will be similar. If you see, it is 473, and over here we are having minus 473. These peaks are there. However, the intensity of the peaks, they are lower. Okay, similarly over here you can you can see there is some frequency, and over here minus 219, you are having the similar peaks, but the intensity are different. Okay, so in a simplistic model, if you want to see, so we can have so if it is mu, this will be mu dash, and this will be mu 0. Okay, sorry, minus of mu and this thing. Okay, so this is the simplistic thing. So peak which is coming at a lower frequency mu 0 minus mu, it is called Stokes frequency or Stokes line or frequency, and at mu plus mu 0 plus mu, this is called anti-Stokes line or anti-Stokes frequency. Okay. So in Raman scattering, we are basically interested in understanding this two lines, Stokes line and anti-Stokes line. So any of this two, it can be either the Stokes line or the anti-Stokes line, they can be analyzed. In absorption spectroscopy and in fluorescence or the luminescence spectroscopy, we have seen that they can be used for the determination of the concentration of the analyte in a particular solution. That means the absorption spectroscopy and the fluorescence or the luminescence spectroscopy or the phosphorescence spectrometer, they can be used for the determination of concentration of the analyte. Okay. Also, previously, so this is quantitative analysis. Also, I had said that in spectroscopy, each molecule, they will exhibit a typical property. Okay. So that can be used for the identification of the analytes. Okay. So that is qualitative analysis. Okay. So just like the previous just like the previous spectroscopic techniques till now, whatever we have discussed, the Raman spectroscopy, it can also help us in qualitative and quantitative analysis of the analytes. Okay. So if you see these peaks, the height of these peaks, they can provide us information about the concentration of the analyte in a particular solution. So what we need to do, again, just like in what we did in this UV visible spectrophotometry, we need to make a standard curve, and from that standard curve we will find out the intensity of the Raman scattering also, and from there we can find out what is the concentration of the solution over there. Okay. Further, how much deviation this mu, how much deviation mu 0 plus minus mu, how much deviation of the frequency is happening from the Rayleigh scattering, that positional shift, it will also give you, it will give you the information about the molecule. Okay, it will give you information about the molecule. Okay, so if you see the distance between this peak, which I am marking, this sharp peak, and the distance between this sharp peak, both of this, if I say this is mu1, this will also be mu1. Okay. So over here, how much amount of deviation is happening from this Rayleigh scattering, that is specific to a certain molecule. Okay, if I use another material, then it will be having a simple, it will be having a different type of scattering properties. Okay, now for a diatomic molecule, there is only one type of movement. Okay, they are vibrating. Okay, so for a diatomic molecule, you will be having three spectral lines. One is Rayleigh scattering, one is Stokes line, and the another is anti-Stokes line. Okay. Now, if you look into this Raman shift, it is given in centimeter inverse. Okay. So, we are having, if you see, we are having mu minus mu 0. So, that means on the left hand side, the frequency is low. Since the frequency is low, the energy content will also be low. Whereas the anti-Stokes line, over here in this region, the frequency is high. Oh, sorry, the energy is high also. Energy frequency is low, energy is low, and when frequency is high, energy is also high. Okay, why this is so? This is because E equals to h mu, we all know. So when mu is high, E will be high because E is directly proportional to mu. Okay. Also, sometimes what happens is that you may get this thing in wavelength. You may get numericals or something like that in wavelength form. So we know E equals to h of mu, which is equals to h of c by lambda. Okay. So you can get this thing. However, in this case, if you see Raman shift centimeter inverse. So centimeter inverse, it is a unit of wave number. Okay, so what is wave number? Wave number is 1 by lambda. So this energy is equal to hc into mu bar, which is the wave number. Okay, you please note down this information. Energy equals to h mu, mu is equal to c by lambda, which is equal to hc mu bar, which is the wave number. So wave number is given by 1 by lambda. Okay. Now if you see over here, if I say that there is a Raman shift, if I say that there is a Raman shift, I am basically talking about the wave number displacement. I am talking about the wave number displacement. Okay. So the Raman effect, it is basically based on the scattering of the light. Okay. So this is the third type what we are talking. First one was the absorption. Second was luminescence. Okay. That include both fluorescence and phosphorescence. And third, we are introducing scattering. Are you getting my point? So Raman effect is based on scattering of light, which includes both elastic scatter, which is called Rayleigh scattering, that occurs at the same wavelength as that of the incident light, and inelastic scatter, which is called the Raman scattering, at different wavelengths due to the molecular bond vibration. Okay. So am I clear till now?
Yes, sir. But I had a question, sir.
Yeah, sure.
Why is the intensity of anti-Stokes lesser than Stokes?
It depends on the molecule. It depends on
Okay,
the
it is
molecule.
dependent on the.
So if it is a what do you call? It is a molecule which is a diatomic molecule, then it may have the same intensity, or it may be the reverse. So it all depends on the characteristics of the molecule.
Okay, so this is not a general trend. Okay,
No,
it's
no, no. This is not a general trend.
okay, sir.
This is
Okay,
just
sir.
to show you where the Stokes line appear and where anti-Stokes line appear. Okay.
Okay, sir. And what does the displacement between the lines, like the distance between the two peaks, what does that signify?
The distance between these two lines. See,
Yes,
here
sir.
what you have to see is the distance between any of the line with that of the relic scattering. So
Really?
this is the important parameter. Okay. So this tells you the delta energy between the two levels. I will come to that in the next slide. Okay.
Okay, sir.
And that will be clear over there.
Okay.
Now, if you see, this is the energy diagram. Okay. So we are having different levels. So from the zero level, if your this thing, if you irradiate the molecule with the with a h mu naught radiation, say this one, the electron from here will go to the higher energy level, which is regarded as the virtual energy state. Okay, virtual energy state. And then most of these molecules, it will come back, these are not molecules, the electrons, they will come back to the ground state having same frequency. However, we have seen energy is directly proportional to the frequency, so there is no change in energy. With whatever energy you are incidentating the molecules, the electron is absorbing all this energy, going up to the virtual energy state, and from there it comes back to the original state, and it releases some of the energy in the form of H mu naught. So whatever the energy is being absorbed, the same energy it is being what you call, it is being released. Okay, hence it is called elastic scattering. Okay, so it is not putting anything. So there is so if you look into the Raman shift, the change in energy is zero. Okay, the change in energy is zero. Next, what happens in Stokes Raman? It is having H mu naught. You are again doing the same phenomena. You are making the sample incident with H mu naught radiation. It goes to the same level. Okay. Then, while coming back, it retains this delta E. Okay. It is not releasing all the energy. Are you getting my point? So, since it is not releasing the energy, that means what is happening? E is proportional to the mu. It is retaining some E, delta E. So, it will radiate at one energy somewhere over here, which will be H mu naught minus of mu, which will be corresponding to this energy. Are you getting my point? So this will be your delta E, which will be retained. Okay. However, in some cases, there might be some infrared absorption which will automatically move the electron to somewhat a higher vibrational energy state. Then it goes up and from there it comes down. Now, if you see this much amount of energy it has gained. So, in this case, it will be delta E, which is equal to H of mu naught plus mu. Are you getting my point? So, what we are doing? We are looking into this mu 0 plus. Over here, we are having this Raman shift means mu bar minus mu, and here anti-Stokes means mu bar minus mu, because Raman shift is in centimeter inverse, and I already told you centimeter inverse is lambda, it is in nanometer, its unit is nanometer, wave number, its unit is centimeter inverse, that means 1 minus 1 by lambda. Are you getting my point? Now is it clear? Now whatever the distance, you see this is the difference over here, delta E. So what is happening? The change in this vibrational level, where it is coming and going, if it is starting from the same vibrational level and coming back to the same vibrational level, then it is not retaining any energy. In Raman scattering, or the Stokes Raman scattering, it means it is retaining some energy. The electron, it is retaining some energy. It is not settling down to the zero electronic level. Whereas in anti-Stokes, it is releasing more of energy. Whatever it has gained, from there also it is releasing more of energy. Okay. So that's why you are getting this delta E equals to H of this thing. And if you look, they are having same distance, because the what you call delta energy of each of these electronic states, not stages, states, they are same. Okay. Anything else? Am I clear?
Yes, sir. Yes, sir.
Okay. Anyone else? No? Okay. So, Raman spectroscopy, it is quite often been compared with the IR spectroscopy. Okay. Over here, the IR spectroscopy, it is sensitive to heteronuclear functional group vibrations and the polar bonds. Okay. Especially OH stretching in water. Okay. Whereas Raman spectroscopy is sensitive to homonuclear molecular bonds such as CC, C double bond C, C triple bond C, etc. Okay. So IR spectroscopy, it is sensitive to heteronuclear functional group vibrations, whereas Raman spectroscopy, it is sensitive to homonuclear molecular bonds. Okay. However, if you plot the curves, you will find that suppose this is the wave number. If this is the intensity, then this wave number, if you plot, then you will get peaks at same location in both IR and Raman spectroscopy. Okay. but the sensitivity of the peak height would be different, because both of them, they are what do you call, absorbing, or they are showing the what do you call, spectroscopic characteristics by different ways. Okay. Iospectroscopy, it is basically following the it is basically a absorption spectroscopy. Okay. Whereas Raman spectroscopy, it is your scattering spectroscopy, scattered spectroscopy or scattering spectroscopy. Okay. So this is the schematic representation of a Raman, simple Raman spectroscope. Okay. So over here we are having a laser. Laser is being what do you call, manipulated so that a concentrated uh, laser beam, it falls onto the samples, and at a 90-degree, what happens, uh, we collect this laser information, this light information what are being transmitted, then there we place a filter, and then we have the of using these filters, there is a breakdown of the, or the decomposition of the bright light, and then we have the detector, and from there we get this spectrograph, spectroscope, big information. Okay.